Last time we introduced the thought process for how to solve thermodynamic problems without data. So remember that without data is the key part. You should always double check first to see if you have data. If you're studying water or another commonly studied component, especially if it's a single component nowadays, the experiments have already been done. So you want to refer to those experiments if you can. But later on in this course, we'll be talking about mixtures. When you have a mixture and the thermodynamic properties are a function of the composition, it's just not realistic, even for a very common mixture like water and ethanol, for the experiment to be done at every composition of interest. And you can imagine how, as you go to 3 components, 4 components, oftentimes it just gets less and less likely that you have the exact thermodynamic data that you need. So these processes are not as important for single component mixtures because, as I mentioned, that you usually have that data available if it's a single component. But studying single component systems are very useful in the sense that you can double check or validate your models for the single component case before extending them and making predictions about the multiple component case. So remember how crazy it got with the calculus for a second. Remember, always bring it back to relating what you do know, relating what is known to what you seek to know, to what is sought. So all these calculus manipulations that you do, that's always the goal, is trying to express a thermodynamic property in terms of something that you can measure. So again, remember that the measurable properties, measurable, we are talking about P, V, and T. And for non-measurable, we are talking about the other 5. Well, I won't say non-measurable, I'll say more abstract properties. So these are not easily, you could measure them, but not easily. So we've got H, A, U, S, and G. So 8 properties, and we'll talk about some interrelationships between them. So here I've written a summary of the useful calculus properties that we used last time, some of the useful ones. I won't cover derivations for any of these. If you're interested in where these identities or where these rules come from, I'll refer to you to your multivariable calculus textbook. Here we'll just focus on what we need them for and useful mnemonics to remember them. So the triple product rule takes 3 variables, 3 state variables, and all I do is I'm just remembering cycling through. So I put the x down there, put the z into the derivative, put the y up there. So just cycling through. If I multiply those 3 partial derivatives, I get a result of -1. This rule, I'm not certain what it's actually called. I like to call it the reciprocal rule. It reminds me that I can take the reciprocal of any partial derivative, and then that flips the positions of the dependent and independent variable. So dx dy at constant z becomes 1 over dy dx at constant z. The expansion rule introduces 2 new variables, k and l, into the equations. And here the mnemonic is that the dk's kind of cancel out to get me back to my original dx dy at constant z. And I can do that again twice. And then my identities, dx at constant y. So any change in a variable upon changing that same variable by any amount will always be 1-to-1. So I like to not memorize these, but rather rationalize them. And similarly, I can say that the change in any variable, if I hold that same variable constant, so dx dy at constant x is always 0 because x is being held constant, and therefore it won't change. I would put these properties in a place that is easily accessible to you, because we're going to come back and use these quite frequently. So just summarizing what we derived last time, remember we had a Joule-Thomson valve, and we wanted to relate the change in temperature upon an isenthalpic expansion of gas. We said that dt was equal to the partial of t with respect to p at constant h times dp. And through a series of derivations, series of steps in the derivation, we got this reduced to, remember, we don't know what t is a function of p and enthalpy is necessarily. So we want to relate it in terms of something that we know. So you can relate it to the specific volume, the temperature, the partial of specific volume with respect to temperature at constant P, all over Cp, the heat capacity, and dP. And if we wanted to actually calculate what the change in temperature is, we could simply integrate both sides. So this derivation is actually fairly common, and for that reason, this entire thing out front is given a special name. This is called mu JT. So this is the Joule-Thomson coefficient as equal to this thing. So this is also something that you don't have to rederive. Also put this in your summary of notes. So the Joule-Thomson coefficient is equal to all this stuff. Notably, it's equal to 0 for an ideal gas, and we showed the derivation of that last time as well. So today, my plan for the first video is to go into a little bit more detail about some of the other tricks that I used in this derivation. And the first couple tricks, or the first class of tricks I want to talk about is called the fundamental property relationships. Fundamental property relationships. All right, so we have to start with, we'll start with one, and then they all kind of derive from each other quite nicely. So the first one that we'll derive is the one for internal energy, which is U under bar, molar internal energy. So start by imagining, we do this all the time in thermo, a piston cylinder device, and do an energy balance on that piston cylinder. So it's a closed system. So again, we're talking about the gas inside, and we are changing the volume of it by moving the piston up and down, and therefore the pressure. Our energy balance is going to simplify to delta U plus delta KE. We're going to cancel that because there's no change in kinetic energy, plus delta PE, no change in potential energy, is equal to Q plus W. So again, that's just the basic closed form energy balance with kinetic and potential energy terms canceled out. I'm going to convert this to a differential form. This is going to be more convenient to work with. So shrink this change in U down to, take the limit as it goes to 0. So du is equal to dq plus dw. And then I'm going to say that dq was defined in terms of what enthalpy is. So remember, the definition of enthalpy is ds is equal to dq for a reversible process over T. This piston cylinder system is a reversible process if we move the piston slow enough and the other 4 criteria are satisfied. We could say that is a reversible process. So we can simply solve for this dq rev, call it dq simply, and say that dq is equal to TdS. Oops, I didn't do the underbars yet. Let me erase that. So TdS, and then work, there is no flow work and there is no shaft work either. So the work that we have is the expansion or compression of this cylinder. So du in this case is minus PdV, right, because the shaft work cancels out. And then du can stay as it were. The only thing that I'm going to do is now change these extensive variables into intensive variables by dividing through by the moles or the mass that are inside that cylinder. So I'm left with du is equal to T ds minus P dV. And this is our first fundamental property relationship. You might have seen this definition in your Thermo 1 class. Importantly, so I derived it for a very specific system of a closed piston cylinder. But if you look at this equation, it only has 5 intensive state properties. So it's got molar internal energy, temperature, molar enthalpy, pressure, and molar volume. These are in terms explicitly in terms of all state properties. And this means that, importantly, this equation is not just valid for a piston cylinder, proper T's should be, but for any process, any thermodynamic process. So remember, state properties don't depend on the path, they only depend on the start and the end points. This is our first fundamental property relationship. Now from there, we can go further and define enthalpy, molar enthalpy, H. That is defined as U plus PV. So that's just the definition of what enthalpy is. And now I can take the total derivative of this expression to get an analogous expression for dH. So taking the total derivative gives me dH under bar is equal to du plus, now I have P times V. What I have to do there is I have to do the chain rule. So I have to keep one constant while I take the derivative of the other one. So that's P dV plus V dP. So remember, look up the chain rule if that step was confusing. Chain rule. And now I'm going to insert the expression for du. So remember that du was TdS minus PdV. I've got a minus PdV plus a PdV. So the PdVs cancel, and I'm left with dH is equal to TdS plus V dP. This is our second fundamental property relationship that'll become important. Two more fundamental property relationships. We haven't dealt with Gibbs free energy and Helmholtz energy a lot quite yet, but Gibbs free energy will be a very important thermodynamic property coming up. So we'll introduce it here. This is another concept that is very poorly defined as a conceptual thing. So just take it as it's defined mathematically for now. Gibbs free energy is defined as enthalpy minus temperature times entropy. So again, taking the total derivative, dg is equal to dH minus T ds minus S dt. Plugging in my expression for enthalpy now, which I just did, so TdS plus VdP, plugged it in there for dH. The TdS's cancel, and I'm left with my third fundamental property relationship of dg is V dP minus S dt. All right, one more. Should be getting the hang of these now. The last one is for Helmholtz energy A, which is equal to internal energy minus Ts. Go ahead and pause the video and see if you can derive your fundamental relationship for Helmholtz energy. It's the same thing that we've done, so take the total derivative. So dA is equal to du minus T ds minus S dt. Plug in my expression for du, and I'm left with dA is equal to minus PdV minus S dt. All right, so I'm going to put a box around all these. Again, remember, you want to summarize these four fundamental property relationships because they will be important in the next video and to come. So again, don't get too caught up on like fundamentally why these expressions are the way they are. Remember, these are going to be tools to relate what we want to know to what we do know.